So this chapter is to some extent is similar to chapter 12, where we have studied kinematics of a particle. Now we are studying kinematics of a rigid body. So let's understand what's the difference between a particle and a rigid body. We'll come back to this quiz later. So a particle has mass, but we neglect the shape and size of the particle. On the other hand, rigid body has mass, shape, and size. Particles cannot have rotation about its own mass center because they do not have shape and size. On the other hand, rigid bodies can have rotation about its mass center, and we need to consider that in our calculation for the design. What are the applications of rigid body kinematics? So look at this amusement ride. Passengers on this ride are subjected to curvilinear translation since since the vehicle moves in a circular path, but they always remains upright. Now, if we know the angular velocity of the rotating arm, how can we determine the velocity and acceleration experienced by the passengers? And why would we want to know these values? Does each passenger feel the same acceleration? Answers of this question can be found uh, during later in the class. Second set of application is gears, pulleys, and cams. These are different members. They transmit the motion from the driver to driven. Now, the angular motion of these objects must be understood properly to design the system. To design, to do this design, we need to relate the angular motions of the contacting bodies that rotate about different fixed axes. How is this different than analyzing in the analysis that we have done earlier in chapters? There are cases where an object cannot be considered as particle. That means we need to consider the shape and size of the body, and also the rotation about the body with its mass center requires a different approach. For example, for the design of cams, gears, and links in the machinery, rotation of the body is an important aspect in the analysis of motion. We will now start to study rigid body motion, and our motion will be limited to planar motion only. That means rigid body rotates in 2 dimension only. There is no 3 dimensional rotation or translation. A body is said to undergo planar motion when all parts of the body move along the paths equidistant from a fixed plane. So next topic, we are going to study about different types of rigid body motions. So let's consider this is our rigid body, an elliptical body, and consider 2 points A and B on rigid body. Now, if the motion of the body is as shown in this slide, where the body moves in linear direction and there is no change in relative position of A with respect to B. In this slide, you can see that this RA/B is position of A with respect to B. And this vector remains unchanged when body moves from left to right. And the green lines indicate the path taken by the body. In this example, if we set up our coordinate system as shown in the figure here, where x is horizontal and y is vertical, then when we can define the position of point B using a position vector RB. And after some time, when body goes from left to right, we can define the new position of point B using position vector RB1. So if we know how long it takes for the body to go from left to right, then we can calculate the velocity of this body for point B by taking the rate of change of position vector with respect to time. So when we do dRB by dt, that gives us the velocity of point B. Once we know the velocity of point B, we can also calculate the acceleration of point B by taking the time derivative of velocity. But how about point A? How can we calculate the velocity of point A if we know the velocity of point B? Well, it's very simple. because there is no change in A with respect to B. So the position vector from A to B is same on left and right hand side. That means velocity of B is same as velocity of A, or in other words, velocity of A is same as velocity of B, and also the acceleration of A is same as acceleration of B. So when body has this type of motion where all the points of the body have the same velocity and acceleration, then this motion is known as translation motion. It doesn't have to be perfectly horizontal. It can also be at an 45-degree angle, or can be vertical, can be going left or down. But as long as all the points on the body, they have the same velocity and acceleration, that motion is known as translation motion. There are two types of translation motion. One is rectilinear translation, where the motion of the body can be expressed as straight lines. And the second one is curvilinear translation, where the motion of the body is along curvature, but still there is no change in velocity between 2 points. So this is also a type of translation, which is curvilinear translation. In fact, in that first example of amusement ride, passengers go through the curvilinear translation. Next type of motion for the body is pure rotation. So consider this body once again, and in this vertical line, which is an axis, and this body rotates with respect to this axis, counterclockwise direction. Points A and B are on the axis of rotation, so they do not have any change in their position with respect to time. That means their velocity and acceleration are zero. So in this example, velocity of B is same as velocity of A, and acceleration of B is same as acceleration of A, and their values are zero. Having said that, all the points which lie on the axis of rotation, they do not have any velocity and acceleration. But what about points A and B are not on the axis of rotation? Let's consider that point A is farther away from the axis of rotation, and point B is closer to the axis of rotation, but none of them is on the axis of rotation. In that case, velocity of B and A are not same, and so as the acceleration. So how do we calculate the velocity and acceleration of points with respect to the axis of rotation? We are going to derive this equation shortly in our today's class. But at this point, just remember that when the body is under pure rotation, all the points which lie on the axis of rotation, they do not have any velocity and acceleration, and all other points, they do not have the same velocity and acceleration if they are not at the same distance from the axis of rotation. If this point is at the same distance from the axis of rotation as point B, then yes, it will have the same velocity and acceleration. But as long as the distance is not same, velocity and accelerations are not same. So as you can see that B is closer, so it has different value of velocity compared to A, which is farther away from the axis of rotation. Third type of motion that rigid body can have is general plane motion. So look in this example, sorry, there was some issue with the screen capture software. Anyways, so we were talking about general plane motion. So look at, in this situation, the motion of the body from left to right. Now this motion is not only translation or rotation, but it's actually the combination of translation and rotation. We can break this down. If we draw the path taken by point A and B, then it looks like as shown in the slide. So this body is undergoing translation and rotation, and that type of motion is known as general plane motion. We can actually break this motion down into two separate segments. So first, only translation of the body, it goes from left to right, and then next step is rotation of the body. So general plane motion is combination of translation and rotation. So, so far we have studied that there are three types of planar rigid body motion. Translation. Further, translation can be divided into two categories. There is rectilinear translation along straight line and curvilinear translation along curved path. Second type of motion is rotation about a fixed axis, and the velocity and acceleration of the points on the body depend on their distance from the axis of rotation. And third type of motion for rigid body is general plane motion, where body undergoes both translation and rotation, as shown in this slide. Next few slides have the textual explanation of what I have already said. So you can just go through them, read the description, which I have already explained in the previous slide. So let's look at this real life example of slider crank mechanism. This mechanism is used in automobile internal combustion engines. It is used in certain types of pumps and also used in locomotives. This mechanism is an excellent mechanism to explain the different motions of rigid body, because all the elements of the mechanism, they undergo different types of motion. So the main elements of the mechanism are, this is called the cylinder, which does not move. So there is no velocity and acceleration. This is piston, which slides. Now piston slides only in horizontal direction. So piston has pure translation motion. This red and green circle is called crank, and it undergoes pure rotation. So crank rotates with respect to its center, and this brown element is called connecting rod, which undergoes both translation and rotation. So if you pay attention to the motion of the connecting rod, it slides as well as it rotates. So it undergoes general plane motion. This slide has the same example with the description about different types of motion for slider crank mechanism. We have already discussed this point that when rigid body has translation motion, all the points on the body, they have the same velocity and they have same acceleration. Now in chapter 12, we studied that if rigid body undergoes only, or rigid body or particle has only translation motion, how can we calculate the position, velocity and acceleration of the particle? We are already familiar with these equations. However, these equations are applicable only when the acceleration is constant. If it is not constant, then we have to do derivation or integration to find the velocity or acceleration. So these equations are applicable for pure translation. Now, what about pure rotation? When body rotates, how can we define the position of the body, its velocity and acceleration? So that's what we are going to discuss next. So consider this example one more time, and consider this red and green crank which undergoes pure rotation. So let's separate only that part, crank part, and this is the disc, which you can say it represents the crank. Now when it is pure rotation motion, we need to use different variables than pure linear motion. So for linear motion, we use variable s for position, v for velocity and a for acceleration. For rotational motion, we use angle theta to define the position. We use omega for angular velocity, and we use alpha for angular acceleration. This slide compares rotational motion variables with linear motion. So if we do one-to-one comparison, then theta is something similar to s for linear system, omega is similar to v for linear system, and alpha is similar to a acceleration for linear system. So let's say that our origin is at O. X is horizontal and y is vertical. And this line is our reference line. That means with respect to this line, we define the position of all the points on the disk. So point P at the given instant, its position is defined using angle theta. Now after, let's say, 10 seconds, disk rotates and point P moves from here to here. You can look at my cursor, and this angle is d theta, which is 10 degrees in 10 seconds. So what is the angular velocity of the disk? In order to find the angular velocity, we need to take the derivative of the position with respect to time. So omega is d theta by dt. Similarly, to calculate acceleration, we need to take the time derivative of velocity. So alpha is d omega by dt. So these are the terms which are used for rotational motion. That means now we can derive all the equations that we have derived for only translation motion for rotational motion. It's very simple. We just need to replace all these variables from translation motion equation by equivalent rotational variables. So we need to replace all s position by theta, v by omega, and a by alpha. So now we will have three more sets of equation for rotational motion, where omega, which is final angular velocity, is equal to omega 0, which is initial angular velocity, plus alpha c, which is angular acceleration multiplied by time. C stands for constant acceleration. Similarly, we have final position theta is equal to initial position theta 0 plus initial angular velocity multiplied by time plus 1/2 alpha t square. And we have omega square, which is final angular velocity, is equal to initial angular velocity square plus 2 alpha c theta minus theta 0. You will be given all these equations for the final exam, so you don't have to worry about memorizing them, but these equations are just a reflection of translation into rotation. Let's talk about the units. So for rotational motion, we use radians for theta, then omega is radians per second, and alpha is radian per second square. Okay, this, and we consider counterclockwise rotation as positive for omega and same for alpha. And you know that one revolution is equal to 2 pi radians. So you can easily convert, if the values are given in degrees, into radians. So 1 degree is equal to pi divided by 180 radians. Okay, we have already discussed these equations. Now let's consider this example of rotating disk. The plane of the disk is in xy plane, and z-axis is perpendicular to the plane of disk. And let's say the disk rotates in counterclockwise direction. Consider this black point P at the perimeter of the disk. Now we are interested to calculate what is the velocity, surface velocity v of this disk if we know the angular velocity omega for the disk. By the way, what is the direction vector for angular velocity? So if the angular velocity is counterclockwise with respect to positive z-axis, to find the direction for angular velocity, we need to apply right hand rule. Take your right hand, bend the fingers of your right hand in the direction of rotation, and in that case, the thumb defines the positive direction for the angular velocity. So for this example, the angular velocity has direction in z direction. So if the angular velocity is, let's say, 10 radians per second, we need to write it as 10 k, where k is the unit vector in z direction. In order to find the velocity of the point P, we need to look at the disk from the top view. So let's say we are in this position and we are looking the disk from the positive z direction. So if we look it from top view, then we will see this view of the disk, where disk rotates counterclockwise. This is the point of rotation, that is point P. R is the position vector from center of rotation to point P, and V is the velocity of point P. So to the magnitude of the velocity v, if we know the omega, can be calculated by multiplying the magnitude of position vector with angular velocity. So v is equal to omega r, and the direction of the velocity for v is always perpendicular to the position vector, and it points in the direction of rotation. So if the position vector is r as shown in the slide, then v is 90° with respect to r, and it points towards the direction of rotation, that is towards right. We can apply, now to find the direction and magnitude of velocity v, we can also apply right hand rule. So consider this point P here. This is our omega, which is z, and it's rotating counterclockwise, and this is position vector r. Now let's say we do not know the magnitude and direction of v. How can we find it if we know omega and r? This is very simple. Take your right hand with your fingers open. Place your hand in the direction of positive axis for omega, and then bend your right hand fingers towards r. At that time, the thumb indicates the direction of positive velocity. So if you bend your finger towards from omega to r, then thumb indicates the direction of velocity. You can see that thumb points towards right, and so as the velocity vector. That means we can calculate the velocity v using the cross product of omega and r. So if we know omega in this example, if we know r, then v can be computed by omega cross r. And the magnitude of velocity is omega r, and direction is given by this arrow. You can pause this slide and read the description before you proceed. Now let's find out what are the directions of velocity for all these points onto this disk if we look this from the top view and the disk rotates counterclockwise. Again, you can pause and think about it and then proceed further. So this arrow indicates the position vector from the center of rotation to the given point. Velocity is always perpendicular to the position vector and points in the direction of rotation. So this v is the velocity for point, that is the right hand side. For this point, this is the velocity vector. For this point, the velocity vector is going left, and for this vector point, velocity vector is going down. How about the velocity vectors for point A and B? And do they have the same velocity? Think about it. So velocity of A depends on the angular velocity omega and the position magnitude of the position vector from the center of rotation. So for A, the position vector is from the center of rotation to point A, which is RA. For B, position vector is from center of rotation to point B, which is RB. Both the points, they have the same angular velocity but different linear velocity. Linear velocity of point A is omega multiplied by RA, and linear velocity of point B is omega multiplied by RB. Also pay attention to the direction of velocity, that it's always 90° with position vector and points in the direction of motion. Similarly for B, it's 90° from RB and it points in the direction of motion. And you can see that in both the cases, it's same omega but different value of r. That means velocity of point A is more than velocity of point B. We can extend this topic further to define the acceleration of point P. Now point P, if you look at this path followed by point P, then it's a circular path. So P goes through curvature. Now when a point follows a circular path, then acceleration has two components. One is tangential component of the acceleration, and second one is normal component of the acceleration. Tangential component of the acceleration of of P can be defined as AT, where T stands for tangential. It's alpha multiplied by r, where alpha is the angular acceleration and r is the magnitude of the position vector. Similarly, normal component of the acceleration is defined as omega square r, where omega is angular velocity and r is the magnitude of the position vector. We can also apply cross product equation to calculate normal and tangential component of the acceleration. So the tangential component AT represents the time rate of change in velocity's magnitude. It is directed tangent to the path of motion. The normal component of the acceleration represents the rate of change in velocity's direction. It is directed towards the center of circular path. So remember that normal acceleration always points towards the center of rotation. And if you apply the cross product equations, then the acceleration of acceleration of point P has two parts. So alpha cross RP, where alpha is angular acceleration, RP is the position vector, and that's a cross product. This is the tangential component of the acceleration, and this one is the normal component of the acceleration, omega cross RP. It can be shown that this equation can be reduced further to A, which is alpha cross R minus omega cross omega becomes minus omega square and R stays as a vector. So remember, with this equation, this omega is scalar, it's not vector. And total acceleration is combination of tangential acceleration plus normal acceleration. And we can calculate the magnitude of total acceleration using the given equation. This is not new. We have already studied this in chapter 12 when we talked about normal and tangential coordinate system. So this is the procedure that we need to follow while solving problems for rotation about a fixed axis. You can just go through the slide and don't worry, because when we solve the in-class exercise, we will actually do all these steps. So it will be very easy to understand once we solve the problems. Now the last part of the theory portion is, let's talk about these two gears. So we call the smaller gear pinion and bigger gear gear. So now next point onwards, I'll call this pinion and this as gear. So this is the special case of rigid body motion transmission, where for two gears to transmit the motion from pinion to gear, at the point of contact, both the gear must have the same surface speed v and same tangential component of the acceleration at. Again, I repeat, at the point of contact, both the gear must have the same velocity v and tangential component of the acceleration at. Because if that is not the case, then gears cannot transmit the motion from driver to driven. So this is the simplified schematic for gears. So let's call this is gear A and gear B. Gear A rotates counterclockwise and gear B rotates clockwise. So at the point of contact, they have the same surface velocity v. Now we have previously in the lecture we have studied that surface velocity depends on the position vector and the angular velocity. And if they both have the same surface velocity, that means the product of omega and r is constant for gear A and gear B. Having said that, omega A multiplied by RA is equal to omega B multiplied by RB. That means angular velocity of gear A multiplied by the radius of gear A is equal to angular velocity of gear B multiplied by the radius of gear B. This is very useful equation for designing gears. We have discussed that they also two gears, they also have the same tangential component of the acceleration, that is at. So as per that equation, tangential component of the acceleration is the product of angular acceleration multiplied by magnitude of the position vector. So at this point, the position vector, the magnitude of the position vector is nothing but the radius of the gear. Hence, for both the gears, this equation holds true. That is, angular acceleration of gear A multiplied by radius of gear A is equal to angular acceleration of gear B multiplied by radius of gear B. This equation is also useful while designing gears.